Installing mental model for regex. You type a regex pattern and it matches text. Simple, right? But what's actually happening under the hood? Let's start with the basics. A single character like A matches itself. A dot matches anything. Easy. But then you add quantifiers. A star means 0 or more. A plus means 1 or more. A question mark means 0 or 1. Now things get interesting. Parentheses create groups. A pipe means or. So the pattern, the letter A, open paren, B pipe C, close paren, star, D, this matches each of these strings and infinitely more. This tiny pattern is actually a program. It has branching, looping, and choices. And your regex engine needs to execute it. But how? The answer is, it builds a state machine. Specifically, a non-deterministic finite automaton, an NFA. Here's how it works. Every regex gets translated into states and transitions. A single character A becomes two states connected by an arrow labeled A. Start state, accept state, done. Concatenation, chain them together. The pattern AB links the accept state of A to the start state of B. Alternation, the pipe operator, create a new start state with two epsilon transitions. Free jumps that consume no input. One path goes to B, the other to C. Both paths merge into a single accept state. And the star operator? This is where it gets clever. Take whatever you're repeating, add an epsilon loop from the accept state back to the start, and add another epsilon from the new start directly to the new accept, because star means 0 or more. This is Thompson's construction, invented in 1968. Watch what happens when we build the NFA for our pattern. Each piece snaps into a state machine, and they connect like building blocks. The result is a graph. Multiple paths, multiple choices. And that word non-deterministic is key. At any state, the machine might have multiple valid next moves. So how do you run an NFA? One approach, convert it into a deterministic finite automaton, a DFA. A DFA has one crucial rule. From any state, each input character leads to exactly one next state. No ambiguity, no choices. The conversion algorithm is called subset construction. Each DFA state represents a set of NFA states you could be in simultaneously. Start with the NFA's start state. Follow every epsilon transition to find all reachable states. That entire set becomes your first DFA state. Now, for each input character, ask, from every NFA state in this set, where can we go? Collect all those destinations, follow their epsilons, and that new set becomes another DFA state. Repeat until no new sets appear. Every DFA state is just a snapshot of every possible NFA state you could be in at that moment. The result? A machine that processes one character per step. Constant time per character. Linear time total. Blazing fast. But there's a catch. The NFA might have 5 states, but the DFA could have up to 32. 2 to the power of n possible subsets. For complex patterns, this explosion makes DFA construction expensive. So most regex engines don't do this at all. Python, JavaScript, Java, Ruby, they all use backtracking engines. Instead of building a DFA, they walk the NFA directly. Here's how it works. The engine starts at the NFA's start state with the first character of input. When it hits a branch, like an alternation or a quantifier, it picks one path and remembers the other. If the chosen path leads to a dead end, the engine backtracks. It rewinds to the last choice point, tries the other path, and continues. Think of it like exploring a maze. You pick a direction at every fork, hit a wall, walk back to the last fork, and try the other way. For most patterns, this works great. The engine finds a match quickly because the right path is usually the first one it tries. But watch what happens with a greedy quantifier like .star. It matches as much as possible first, then backs off one character at a time. On a 100-character string, that could mean 100 backtracks just for one part of the pattern. Now imagine nesting quantifiers, a pattern like open paren, A+, close paren, plus. At each step, the engine has to decide, does this A belong to the inner group or start a new outer repetition? The number of choices multiplies, and that's where things go very, very wrong. This is REDOS, regular expression denial of service. Take the pattern open, paren, A plus, close paren, plus, followed by the letter B. Feed it a string like a bunch of A's, followed by X. The engine tries to match. It reaches the X, which can't match B, so it backtracks. But every possible way to divide those A's into groups has to be explored. 10 A's? About 1,000 paths. 20 A's? Over 1,000,000. 30 A's? Over 1,000,000,000. Each character you add doubles the work. Exponential time. One carefully crafted string can pin a CPU at 100% for minutes, or hours. The regex never crashes. It's just doing exactly what you told it to. This isn't theoretical. In 2016, a regex in a Stack Overflow post crashed Cloudflare's servers for 27 minutes. In 2019, a single line of regex took down NPM for 6 hours, all because a backtracking engine hit exponential blowup. The fix? Avoid nested quantifiers over overlapping patterns. Use atomic groups or possessive quantifiers. Or switch to an engine like RE2 that uses Thompson's NFA simulation. Linear time, guaranteed. Your regex is a program, and like any program, it can have performance bugs hiding in plain sight. Cognitive architecture updated.